So in this session, we will look at the topic CPU scheduling. So the basic concept of CPU scheduling is that to maximize the to maximize the the basic. So in this session, we look at the concept of CPU scheduling. So to maximize CPU utilization, multi-programming concept was introduced. We have multiple programs in the main memory, and these programs will be executed in concurrent manner in the CPU. So in this session we will look at the concept of CPU scheduling. So the basic concept So in this session we will look at the topic CPU scheduling. Basic concept of CPU scheduling is that we have multiple programs loaded in the main memory, and these programs will be executed in concurrent manner with the CPU, right? So multi-programming concept was introduced to maximize the CPU utilization. Say So in this session, we look at the topic CPU scheduling. Basic concept of CPU scheduling arises from the concept of multi-programming. We have multiple programs loaded in the main memory, and these multiple programs will be executed in concurrent manner in the CPU, right? So the next question arises is which program will be executed and when. So to decide the order of execution of these multiple programs from the main memory, we have to schedule them, right? And this scheduling procedure is called as CPU scheduling. So to maximize CPU utilization obtained with multi-programming, we have to order these multiple programs so that they can be executed in the CPU concurrently, right? So a program may have some CPU instructions, it may have some IO instructions. Like if we have an example, so say we have this one, int main, int a, fp pointer is equal to, which is of type file, f open abc dot txt, and we open this file in write mode, right? And then we write something into this file say f right. Hello. So this instruction, or we are writing hello to this abc.txt file, and then printf hello is written, and then return 0, right? So in this program, int a is a CPU burst. It requires the CPU. File fp pointer equal to f open abc.txt in write mode. So when this instruction will be executed, there is a need to open a file, or there is a need to create a file in the secondary storage if abc.txt is not already present. If it is there, then this file has to open from secondary storage. So some IO operation regarding secondary storage will be required at this particular instruction. So this is, you can say, this is CPU instruction, and this one is IO instruction, and again this one is the IO instruction, because we have to write this string into this file, and that file is present at the secondary storage, right? So again this is the IO instruction, because we need to display this content on the monitor. So at this time, monitor is our IO device which is required. So you can say that CPU, then again IO, then IO, then IO, and then some CPU instruction is there in this program. So we can say that this program is alternate sequence of CPU, IO, 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 and CPU instructions. So a program may contain some CPU instructions and some IO instructions, and these CPU and IO instructions can be executed in interleaved manner, right? The order of these instructions is not defined. It totally depends on the type of program which you have written, right? So the concept here is to understand is that a program may have some CPU cycles or IO cycles, right? So when a program is executing in the IO, if I have another program in the main memory available, I can shift that program into CPU when another process is executing its IO, so that maximum utilization of CPU can be achieved. So this can be the overall structure of any program where alternating sequence of CPU and IO bursts are required. So load, store, add, store, read from file, these are the CPU instructions. Then wait for some IO, then some increment, index, write to file, again some IO instructions are required, then some CPU instructions are required, then some IO instructions are required, and so on. So this can be the overall skeleton of any program, right? So to select a process from the processes in main memory that are ready to execute and allocates the CPU to it, it is the need of your scheduler. So what a scheduler is required to do, first task it is required to do is the select a process from multiple processes which are available in our main memory and allocate it to the CPU, right? Next is CPU scheduling decisions may take place when a process switches from running to waiting state, switches from running to ready state, switches from waiting to ready state, or process terminates. So a CPU scheduler selects a process from the processes in the main memory that are ready to execute and allocates the CPU to it, right? Then CPU scheduling decision may take place when a process switches from running to waiting state. So when a process is going to waiting state from running state, now CPU is idle, and when CPU is idle, there is a need to put another process in the CPU so that CPU will not be idle in the idle state, right? So whenever a process shifts from running state to waiting state, or you can say whenever CPU becomes idle, there is a need to execute the CPU scheduler algorithm or CPU scheduler program, right? So that a new process from ready queue or ready state can be picked up and executed in the CPU. That is the main concept, right? So whenever a process from running state shifts its state, whether it can go in the waiting state or it can terminate or it can go to the ready state. So whenever these events happens, CPU scheduler has to pick up a process from ready state and allocate it to the CPU, right? Another case can be when a process switches from running to ready state. So this transition can happen when an interrupt arises or when a context switch happens because of some high priority process comes to the ready queue, right? Or when the time quantum of running process is expired. So under these circumstances, a process may have to shift from running state to ready state. And when a process is shifting from running state to ready state, again CPU is idle. So when CPU is idle, a new process has to shift from ready state to running state, right? Switches from waiting to ready state. Suppose a process which was waiting in the IO or blocking state, and when this IO is completed, it again shifted to ready state, right? And say this process has the highest priority among all the processes, even its priority is higher than the running process, right? So in that case, the running process has to come out from the CPU, and this newly submitted process which was coming from waiting state has to execute in the CPU immediately, right? So again the CPU scheduler has to pick up this highest priority process which is just submitted to the ready state from waiting state, right? So this is the another case when your CPU scheduler has to execute. Or when a process terminates, so in terminate state, a process will be shifted from running state to terminate state. So when a process is terminating, your CPU becomes idle, and when CPU becomes idle or CPU becomes empty, a new process has to submit it to the CPU, right? So these are the four cases when a CPU scheduling decision may take place. So scheduling under 1 and 4 is non-preemptive. Non-preemptive means when running process will not be context switched by some high priority process, right? So in case of point number 1, switches from when a process switches from running to waiting state. So when a process is going to waiting state, it will not be able to preempt a process which is running in the CPU. Why? Because it will be blocked, right? And when it is blocked, how it can preempt a process which is running in the CPU? Is it right or not? Fine. And point number 4, when a process terminates, again this process is terminated, so it cannot terminate, or it when a process is terminated, it cannot preempt a process which is running in the CPU, right? So 1 and 4 are non-preemptive, 2 and 3 are preemptive. So in point number 2, when a process switches from running to ready state, so when this process which was in the running state and it has been submitted to ready state, now this process can be the next process which is having the highest priority among all the existing processes. So this process has to be selected next to execute in the CPU. So this process may preempt a process which is running in the CPU, right? Point number 3 says that when a process switches from waiting to ready state, again when a process is submitted to ready state, it may be the next process which is having the highest priority among all the available processes. So this may context switch, or this may preempt a process in the CPU. So point number 2 or 3, or from so a CPU scheduler selects a process from the processes in the main memory that are ready to execute and allocates the CPU to it, right? So we have multiple processes or multiple programs in the main memory, and from those programs, CPU scheduler is going to pick up one process that will be executed in the CPU next. So CPU scheduling decision may take place when a process switches from running to waiting state, right? So here we are trying to see that when a CPU scheduling decision takes place, or in other words, when or under what circumstances, or under what events CPU scheduler process will be invoked, right? So we can say that whenever a process leaves from CPU, next process has to be selected to execute in the CPU, because now my CPU is idle, and when CPU is idle, a process has to be shifted from ready state to running state. and it's the job of CPU scheduler to select a process from ready queue to put it into the CPU, right? So it is the task of CPU scheduler to select a process from main memory and put it to the CPU, right? So when a process switches from running to waiting state, there is a need of execution of the CPU scheduler, right? Next can be when a process switches from running to ready state. So from running state, so CPU scheduling decision may take place when a process switches from running to waiting state. So whenever a process comes out from CPU, the CPU is idle. When CPU is idle, there is a need to put next process into the CPU, and it's the job of CPU scheduler, right? Now when a process is coming out from running state, in which state this process may go? If you don't remember the process state diagram, we can have it like this. Is the new state. From new state, it will be submitted to ready state, and from ready state, process will go to running state. From running state, it may go to waiting state, and from waiting state, it may go to ready state, right? So from ready state, a process may shift to running state when it will be scheduled. And from running state, a process may go to ready state when an interrupt is generated, and that interrupt may be because of preemption. Now what is preemption? When a high priority process is existing in the ready state, and that high priority process wants to execute in the CPU, so that already running process has to come out from the CPU. So this expulsion of running state process by some high priority process is called as preemption, right? So we can say that when a high priority process expels out a low priority process from the CPU, so this is called as preemption. So the low priority process is preempted by high priority process, right? So interrupt may be because of some preemption, or it may be because of time quantum expiry. The allocated time quantum is expired, then this running process has to come out immediately, and it will be submitted to ready state, right? From running state, a process may go to waiting state when some IO request is generated. And from waiting state, when IO response is submitted on some IO response, a process will be again submitted to ready state. From running state, a process may go to terminate state, right? So this is your state diagram of a process, right? So we have said that whenever a process comes out from running state, CPU scheduler has to pick up the next process to submit it into CPU, right? So from running state, a process may go to waiting state when some IO is generated, or it may go to terminate state, right? So when a process goes to waiting state or terminate state, this process cannot preempt a running process. Getting it or not? When we are saying that a process, suppose P1 is submitted to waiting state, can this process P1, when it is in the waiting state, preempt a process which is running? No, it cannot, because from waiting state it has to first submit it to ready state. Until and unless a process is not submitted to ready state, it cannot directly go to running state. In the running state, only one transition is there, from ready to running, right? Similarly, when a process P1 is submitted to terminate state, it cannot preempt a process which is in the running state, because there is no transition from terminate state to running state. When a process is terminated, it will not be executed next, right? Another transition can be when a process is submitted from waiting to ready state. Now when a process is submitted from waiting to ready state, there may be chance that this process is having highest priority among all the processes, even the one which is in the running state, right? So in that case, this newly submitted process in the ready state from waiting state will preempt the low priority process which is executing in the running state. So in this case, when a process is submitted from waiting to ready state, immediately your CPU scheduler has to pick up this highest priority process, if this is the highest priority process, if this is, but again your CPU scheduler has to check, right? Check it every time when a process is submitted from waiting to ready state. Yes or no? So in that case, this process may preempt a process in the running state. Similarly, when a process is interrupted from running state, it will be submitted to ready state. So in that case also there may be a chance that this preempted process will be having the highest priority again. So in that case also this interrupted process will again has to submit it to the running state. So in that case also CPU scheduler has to be invoked, right? So overall we can say that whenever your CPU becomes idle or a process comes out from CPU and will be submitted to either waiting state or submitted to terminate state, in these two cases this process cannot preempt a running process, right? Or when a process is having a transition from CPU to ready state, CPU means the running state, CPU to ready state, again CPU scheduler has to be invoked, and this time this process may preempt a running process if it is having the highest priority among all the remaining, or when a process is submitted to ready state from waiting state, again it may preempt, right? So you can say that when a process is submitted from waiting to ready state, again it may preempt a running process, right? So whenever CPU is becoming idle, number one, or whenever a new process is submitted to ready queue, or whenever a process is submitted to ready queue, your CPU scheduler has to work, right? And we have seen that when a process can preempt or when a process cannot preempt a running process. So when a process is submitted to ready queue, it may preempt the running process, and when a process is submitted to waiting or terminate state, it will not be able to preempt the running process, right? So our next point says that when a process switches from running to ready state because of some interrupt, again we have to call the CPU scheduler. When a process switches from waiting to ready state because of some IO completion, again we have to invoke the CPU scheduler, and this time this newly submitted process can preempt a process which is in the running state, and when a process terminates, CPU becomes idle. Again a new process from main memory or ready queue has to be selected by the CPU scheduler, right? So if any event happens out of 1 and 4, they will be like non-preemptive, and event number 2 or 3 are like preemptive events, right? Synchronization among processes is required in case of preemptive scheduling. So some kind of synchronization among processes is required if preemptive scheduling is implemented, right? Dispatcher module gives control of the CPU to the process selected by the short-term scheduler. So a dispatcher is like CPU scheduler selects a process from the main memory, that which process has to be executed next. Say in the main memory we have 3 processes P1, P2, P3. So out of these 3 processes, CPU scheduler will pick up the highest priority process, which is say P2, and its name will be given to dispatcher. Now dispatcher will take this process from main memory and load it into the CPU. So CPU scheduler job is to just pick up or just to select a process from the main memory that this process will has to execute next. Now CPU scheduler job is done, and then dispatcher will take this process from main memory and load it into the CPU. This means dispatcher will load the contents of PCB into the CPU registers, right? So dispatcher involves context switching. Context switching means the contents of CPU registers for the running process will be saved back to main memory first, and then the contents of main memory of the next process which is going to be executed in the CPU will be loaded into the registers of the CPU, right? And then the CPU's mode will be switched to user mode by default mode, and then jumping to the proper location in the user program to restart that program according to the program counter. That what was the last value of program counter, from there only the next scheduled process will be executed or resumed, you can say. So dispatch latency is the time it takes to the dispatcher to stop one process and start another running process, right? So stopping a process means saving the CPU register values into the PCB of that process in the main memory, and then loading the contents of PCB of the next process into the CPU registers, and then changing the CPU mode to the user mode. So this time duration is called as dispatch latency, the time a dispatcher takes to change the process in the CPU. So scheduling criteria may be CPU utilization, turnaround time, waiting time, and response time. So this means whenever we try to develop any scheduling policy, what all parameters we have to consider, right? Our main purpose is to maximize the utilization of the resources, and in this case we are trying to maximize the utilization of the CPU. So CPU utilization has to be maximized. Number one, that means keep the CPU as busy as possible. Throughput is number of processes that complete their execution per unit time, right? So throughput is another parameter which we have to consider. Turnaround time, it is the amount of time to execute a particular process, that is the summation to termination duration. So when a process is submitted to the system and when it is finished, the time duration between these two events is called as turnaround time of that process. So again, the arrival time of that process and when it is leaving from the system. So time duration between these two events, arrival and completion, is called as the turnaround time of that process. Suppose a process P1 is submitted at time 1 second and it is finished at 10th second. So turnaround time for this process is 9 seconds. Right? Waiting time, it is the amount of time a process has been waiting in the ready queue, or it is the time when a process is doing nothing. Right? When a process is executing some IO device, we cannot say that this process is waiting, because at that time the process is actually busy in doing some IO task. So that process is not waiting for some resource. So waiting time actually is the time when a process is waiting to be executed either in the CPU or for some IO computation. Right? So a process is in ready queue which is actually waiting for some resource is called as its waiting time. Suppose a process is waiting for some IO device, then again that waiting time will be included in the waiting time of that process. Right? But when a process is executing in the IO, or it is busy to execute the IO, we cannot say that process is waiting at that time. Right? Response time, amount of time it takes from when a request was submitted until the first response is produced, not the output. Right? So when a process is submitted and when it is getting the first response, so this duration is called as its response time. Suppose a process is submitted at time 1 second and its first response is coming at time 5 second. Response means when this process is getting the CPU. So that duration is called as its response time. So optimization criteria for any scheduling policy can be maximizing the CPU utilization, maximizing the throughput, minimizing the turnaround time, because turnaround time is the time duration between submission of an process to the system and till the completion of the process. So we want to complete our processes as early as possible. So if process is finished as early as possible, its turnaround time is obviously minimized. Minimum waiting time, right? And minimum response time. So to optimize any scheduling criteria, these are the parameters we have to consider. Now first scheduling algorithm can be first come, first serve. That means according to the arrival time of the processes, we are trying to schedule the processes with the CPU, right? So the process which is coming earliest will be of highest priority. So FCFS can be easily implemented using a FIFO queue. When a process enters the ready queue, its PCB is linked to the tail of the queue, right? It means, say we have something like this. This is my main memory. And in this main memory, these are the processes. So this is PCB 1, PCB 3, PCB 4, PCB 5. PCB means process control block, right? So, and their arrival time are 0, 1, 3 and 7, right? So the first process is PCB 1, that is P1 say, and this is my FIFO queue. I have a queue with me. So in this queue, this is the start. So at time 1, a new process P3 is submitted to the system. So it will be appended at the tail of this queue, right? So this is the front and this is tail, you can say. So you can implement this queue with the help of linked list also, right? So this is the start, and next to this process will be submitted PCB3, and next to it will be PCB4, and then PCB5, right? So whenever a new process is submitted, it will be appended in the tail, right? And processes are executed starting from the start pointer, right? So this is how we can implement FCFS. So when CPU is free, it is allocated to the process at the head of the queue, that is your start. So let's have an example to understand FCFS better way. We have three processes with us, P1, P2, P3, and their burst time are 24, 3 and 3 respectively. Suppose that the processes arrive in the order P1, P2, P3. Draw the Gantt chart for this system and calculate average waiting time, average turnaround time and average response time, right? The point here to note is processes are arriving in the order P1, P2, P3 and their arrival time is not given explicitly. So we are assuming that their arrival time is almost 0. Almost 0. Say P1 has been arrived at time 0, P2 is arrived at time 0.00000001, P3 is arrived at 0.000000000001, right? So overall their arrival time is almost 0, but P1 has been arrived first, then P2 and then P3. So we know the order, right? So this can be the Gantt chart of the system. P1 has been arrived first at time 0 and its burst time means the CPU time. Burst time means CPU time, and its CPU time is 24. So P1 will be finished at 24th second. Then P2 is arriving, right? Then P2 is arriving. P2 burst time is 3 seconds. So P2 will start from 24 and it will end at 27. P3's burst time is again 3. So P3 is starting at 27 and it will finish at 30, right? So this is the overall Gantt chart of the CPU, right? You can say the timeline diagram of the CPU. So we have to find out the average waiting time, average turnaround time, and average response time. So average waiting time says that the time a process is waiting. So average wait, or we can say waiting time of P1 plus waiting time of P2 plus waiting time of P3 divided by 3 will give you the average waiting time of the system. So waiting time for P1 is 0 because it has arrived at time 0 and it got the CPU at time 0 only. So P1's waiting time is 0. P2 was also submitted at time 0, almost 0, and it is allocated the CPU at 24th second. So up to 24th second P2 has to wait. So waiting time of P2 is 24. Similarly P3 was also submitted at time almost 0 and it got the CPU at 27. So waiting time of P3 is 27 seconds and average waiting time will be 0 plus 24 plus 27 divided by 3, that is 17, right? Average turnaround time will be turnaround time of P1 plus turnaround time of P2 plus turnaround time of P3 divided by 3. So turnaround time says that the submission time and the completion time. So this difference between submission time and its completion time is called as the turnaround time of that process. So process P1 is completed at time 24th second and it was submitted at time 0. So its turnaround time is 24 minus 0 plus turnaround time of P2. So P2 finishes at 27 second and it was submitted at time 0. So 27 minus 0 is the turnaround time of process P2. Process P3 is submitted at time 0 and it completes at time 30. So 30 minus 0 is the completion time, turnaround time of process P3. So process P1 turnaround time plus process P2 turnaround time plus process P3 turnaround time divided by 3 will give you the average turnaround time, and that is 20.33. Average response time, that when a process is submitted and when it is getting the first response, right? So process P1 was submitted at time 0 and it is getting the CPU first time at time 0 only. So response time of process P1 is 0 second. Process P2 was submitted at 0 and it is getting the CPU first time at 24th second. So that of P2 will be 24. For P3, 27 minus 0, that is 27, divided by 3 is equal to 17. So this is the average response time of process, average response time of the system, right? Let's have another example. So considering example 1, that is our previous example, this one, suppose that the processes arrive in the order P2, P3 and P1. So this time their order has been changed. Again we have not given the arrival time values, so we are considering that they are arriving at almost time 0. Draw the Gantt chart for this system and calculate average waiting time, average turnaround time and average response time. So this time Gantt chart will look like this. Process P2 burst time was 3 seconds, P3 burst time was 3 seconds and P1's burst time was 24 seconds. That is here. P1 burst time was 24, P2 and P3 was of 3 seconds each, right? And their order are P2, P3, P1. So first of all, P2 will be executed for 3 seconds, 0 to 3. Then P3 will be executed for 3 seconds, 3 to 6. And then P1 is executed for 24 seconds. So from 6 to 30, right? So waiting time for P1 will be this time 6 seconds. For P2 it is 0. For P3 it is 3. So average waiting time will be 3. Average turnaround time. So turnaround time of P1 is 30 minus 0 because it is completed at 30 seconds and it was submitted at time 0, almost 0. So 30 minus 0 plus turnaround time for process P2, that is 3 minus 0. Process P2 is completed at 3rd second and it was submitted at time 0. So 3 minus 0 plus turnaround time of P3 is 6 minus 0 and then divided by 3, it will give you 13. Average response time. So response time of process P1 is 6 seconds plus that of P2 is 0 and that of P3 is 3. So it comes out to be 3. Now if we compare the values of this problem with our previous problem, so average waiting time was 17, average turnaround time was 20.33 and average response time was 17. So 17, 20.33 and 17. In this case, we are having the processes with same burst time except that their order is changed, and because of that average waiting time comes out to be 3, which was 17 in last case, and average turnaround time comes out to be 13, which was 20.33 in last case, and average response time is equal to 3, which was again 17 in the last case. So in this case all these 3 parameters having very less value as compared to previous example. So what we can say? What is difference between this problem and our last problem? If you look at the burst time of these processes, so this time what we have done that we have executed P2 and P3 first and their burst time was 3. So the highest burst time process P1 was executed in the last. So from here we can say that if we execute smaller processes first, the overall waiting time will be reduced, the overall turnaround time will be reduced, and overall response time will also be reduced, right? And this can be understood with the help of our day-to-day life example also. Like in malls, big bazaar, we have separate queue for those who are having only less than 5 items to bill, right? There is a separate billing counter for those who are having only say 5 products with them, 5 items. So here the same concept is applied, that processes with shorter time is executed first, then the overall waiting time, overall turnaround time, and overall response time will be minimized, and hence throughput can be increased, right? So a convoy effect says that short process behind long processes may lead to lower CPU utilization, right? So this is the convoy effect. Many times in some exam they ask that what is convoy effect, directly or indirectly. So we should have some idea about convoy effect, that what it says, right? So if shorter processes waits behind long processes, this leads to the low CPU utilization, and that is called as convoy effect. So our next scheduling policy is shortest job first. That means if we schedule our shortest job first, then overall waiting time, overall turnaround time, and overall response time can be minimized, right? But again, there is issue with it. How we will decide that which process is the shortest? That means beforehand we need its burst time or the burst time of each process, but we cannot predict that what can be the burst time of a process, right? We don't know. If a user submits a process, it never submit the time duration for which this process will be executed. Suppose you just open your Microsoft Office Word. Do you enter for how long you are going to work in this process? No. Suppose you open Windows Media Player. Do you enter some time that after what time you will close this process? No. So operating system will not be able to get the exact time duration of a process, and if I don't have the time duration or the CPU burst time of a process, how can I find out the shortest job? So in practical it is very difficult or almost impossible to get the burst time of all processes, and hence shortest job first scheduling algorithm cannot be implemented fully in the practical scenario, in the real life scenario, right? So CPU burst of process is used to schedule them, Two schemes are there. One is non-preemptive. One CPU gives to the process it cannot be preempted until completes its CPU burst. So a process which is in the running state cannot be preempted by other process while its execution is going on, right? Another scheme is preemptive. If a new process arrives with the CPU burst length less than remaining time of the currently executing process, preempt it, right? So this scheme is also known as shortest remaining time first. So SRTF is equal to SJR plus preemption, right? So when a new process with small CPU burst cycle is submitted to the ready queue, so this process will preempt the one which is executing in the CPU, and this scheme is called as preemptive shortest job first or shortest remaining time first scheme, right? SJF is optimal. It gives minimum average waiting time for a given set of processes. So we can use this scheduling process as a benchmark for all the other remaining processes. We can judge the performance of any scheduling algorithm according to SJF scheduling algorithm, right? It is hard to implement in real-time systems. Let's have an example to understand it. We have four processes with us, P1, P2, P3, P4, and their arrival time are 0.04 P1, 2.04 P2, 4.04 P3, and 5.04 P4, and their burst time are 7, 4, 1, 4 respectively. Fine. Then it is asking that draw the Gantt chart for this system and calculate average waiting time, average turnaround time, and average response time using SJF non-preemptive scheme, right? So SJF non-preemptive scheme says that when a process is executing, it cannot be preempted by other process even if that other process is having less CPU burst time than the one which is in execution state, right? So Gantt chart of this given system can look like this, right? Now you can say that the burst time of P3 is smallest, that is 1. So P3 has to execute first, but here we are executing P1 first. Why? Because at time 0 only P1 is there. At time 0 only process P1 is available in the system, right? At present we cannot say कि after 4th second process P3 will come which will be having burst time 1, right? So at this particular moment at time 0 there is only one process P1 in the system. So obviously this P1 process will be executed first. So P1 will be executed first, and again you can say that now at time 2.0 P2 is available. So at time 2 P1's remaining burst time is 7 minus 2 because 2 seconds it already completed. So remaining time duration of P1 is 5 seconds, and that is greater than P2's burst time. So P2 is having highest priority because the less burst time of P2, but P1 will not be able to preempt it by P2. Why? Because it is non-preemptive SJF algorithm scheme. So because of this, even if P2 is having higher priority than P1 or P2 is having less CPU burst time than P1, still P2 will not be able to preempt P1. So P1 will finish its execution first at 7 second, and at 7 second again check for available processes. So at the starting of 7 second you are having P2 that is arrived at 2 seconds, P3 arrived at 4 seconds, and even P4 is there that was arrived at 5th second. So at 7th second you are having P2, P3 and P4 with you, right? Now you compare the smallest burst time among these processes. So among these P2, P3, P4, P3 is having the smallest burst time of 1 second. So now P3 will be executed. P3 will be executed for 1 second, and at time 8 you will be having P2 and P3 with you. So out of P2 and P2 and P4, P3 is completed, right? So at 8 second P2 and P4 is there, and out of P2 and P4 both of them are having same burst time. So how to remove this conflict? So next priority can be their arrival time. The one which is arrived first will be executed first. So hence P2 will be executed first at 8th. Its burst time is 4 seconds. So it will complete its execution at 12 seconds, and then P4 will be executed after 12 seconds, and it will finish at 16th second. So this is the Gantt chart of this given system. So average waiting time is equal to waiting time of process P1, that is 0, arrived at 0 and got the CPU at time 0, plus waiting time of P2. P2 was arrived at 2 seconds and it got the CPU at 8 seconds. So it has waited from 2 to 8, that is 6 seconds, right? P3 arrived at 4 seconds and it got the CPU at 7 seconds. So its waiting time is 7 minus 4, that is 3. For P4, P4 arrived at 5 seconds and it got the CPU at 12 seconds. So 12 minus 5, 7 is the waiting time of P4. So average waiting time is 0 plus 6 plus 3 plus 7 divided by 4, that is 4. Average turnaround time. So average turnaround time is equal to turnaround time of P1. So P1 was completed at 7 and it was submitted at time 0. So 7 minus 0 is turnaround time of P1. Then for P2, P2 completed at 12 and submitted at time 2. So its turnaround time is 12 minus 2, plus for P3 completed at time 8 and submitted at time 4. So 8 minus 4, that for P4 is completed at 16, submitted at 5. So 16 minus 5 divided by 4 is equal to 8. Average response time. P1's response time is 0, submitted at 0, got the CPU at time 0, plus for P2 got the first time CPU at time 8 and it was submitted at 2. So 8 minus 2 plus P3 7 minus 4 plus P4 12 minus 5 divided by 4 equal to 4, right? So you can compare here average waiting time and average turnaround time and response time with your FCFS algorithm, right? If you execute this system with FCFS, definitely this time will be greater than SJF algorithm for FCFS, right? Another example is the same process set is given, but this time they are asking to implement SJF with preemptive scheme or SRTF algorithm, right? So in this case, what can be the Gantt chart? So process P1 was executed first because at time 0 only process P1 was there. So P1 will be executed at 0.0. At 2.0 process P2 was submitted, right, which is having bus time 4, and at time 2 P1's left bus time is 5 seconds because 2 seconds it has completed, so remaining is 5 seconds. P2's bus time is smaller than P1's bus time, hence P1 is having high priority than P1, P2 is having high priority than P1, so P2 will preempt the running process P1 at time 2. So P2 will be having high priority than P1, so P2 will preempt P1 at time 2, right? At time 4, a new process P3 is submitted. So up to 4, P2 has completed 2 time units. It has started from 2. So up to 4, it has completed 2 units. So remaining bus time of P2 is 2 units. And P3's bus time is 1 unit. So again P3 is having high priority than P2. So P3 will preempt process P2 at time 4. So P3 will preempt process P2 at time 4 and its bus time is 1 unit. So it will be completed at 5. At 5, P4 is submitted, which is having bus time 4. P2 is there, which is having 2 units left bus time, and P1's bus time is 5 units because 2 units it has completed and left bus time of P1 is 5 units. So P1 is having 5 units, P2 is having 2 units, P4 is having 4 units. So out of these 3 processes P1, P2, P4, P2 is having smallest bus time, that is 2 units. So next time after P3, P2 will continue, right? So after P3, P2 will continue from 5 to 7. Then P1 is having bus time 5 remaining, P4 is having bus time 4 remaining. So out of P1 and P4, P4 is having less bus time, that is 4. So P4 will be executed and then at the end P1 will be executed, right? So you can say this is how these processes will be scheduled on the CPU. So this shows the timeline diagram of the CPU, that at what time which process will be executing in the CPU, right? So average waiting time is equal to waiting time of P1, that is in the starting it has waited for 0 second, Then at time 2 it left the CPU, and P1 process got CPU again at 11 second. So from 2 to 11 P1 was waiting, right? So in the starting it waited for 0 second, and after second it got CPU again at 11 second. So 11 minus 2, 9 second. Overall this process P1 is waited, right? For P2, first time P2 was submitted at time 2, it got CPU at time 2, so 0 second it has waited in the starting. Then it went out from CPU at time 4 and again got the CPU at time 5. So 5 minus 4, 1 second overall P2 has waited. P3 submitted at time 4, got the CPU at 4, and then after it has waited for 0 second, right? For P4 submitted at time 5, got the CPU at 7, so 7 minus 5, that is 2, divided by 4 equal to 3, right? Average turnaround time of process P1 was completed at time 16. P1 was completed at time 16 and submitted at time 0. So 16 minus 0. P2 is finished at time 7 or completed at time 7, submitted at time 2. So 7 minus 2 is turnaround time of P2. P3 is completed at time 5 and submitted at time 4. So its turnaround time is 5 minus 4 plus P4 completed at time 11 and submitted at time 5. So 11 minus 5 divided by 4 is equal to 7. So this is the average turnaround time of this system. Average response time for process P1, response time is submitted at time 0 and first time it got the CPU at 0, right? So response time for P1 is 0 plus P2 was submitted at time 2 and it got the CPU at time 2. So again response time of P2 is 0. P3 submitted at time 4 and got the CPU at time 4. So its waiting time is again response time is again 0 plus P4 was submitted at time 5 and got the CPU at time 7. So its response time is 7 minus 5, that is 2. So that overall response time is equal to 0.5. So preemptive SJF performs better than non-preemptive SJF. You can compare. Waiting time here comes out to be 3, turnaround time comes out to be 7, and that of non-preemptive it was 4 was the average waiting time and 8 was the average turnaround time, and response time is 4, right? So preemptive SJF performs better than non-preemptive SJF. Here is the method by which next CPU burst cycle can be determined. Exact CPU cycle we cannot determine, but expected CPU burst time can be calculated with the help of this formula. And what is that? We are saying that Tn is equal to actual length of nth CPU burst. Tau n plus 1 is equal to predicted value for the next CPU burst. Alpha lies between 0 and 1. So the next CPU burst value can be predicted as tau n plus 1 is equal to alpha times Tn that is the CPU burst length in nth second plus 1 minus alpha times the predicted value in the nth second, right? So in nth plus 1 the expected value is depending on the expected or the predicted value and the actual value of the nth CPU cycle, right? So alpha Tn plus 1 minus alpha tau n will give you the next expected or next predicted CPU burst cycle, right? Here we have an example. So Ti is given as 4, 6, 4, 13, 13, 13 and the calculated tau is equal to 10, 8, 6, 5, 9, 11, 12 and so on, right? So using this formula we can calculate the predicted value of next CPU burst, right? So this is an example. Suppose we have a pattern of burst time as 6, 4, 6, 4, 13, 13, 13 and assume the initial guess is 10. Predict the next burst time alpha equal to 0.8, right? So we have tau n plus 1 is equal to alpha Tn plus 1 minus alpha tau n, where alpha is 0.8, that is given, and Tn given was 6 initially and tau n given was 10 initially. It is saying that assume the initial guess is 10, that is the tau n, and Tn initially is 6. So tau n plus 1 is equal to alpha, that is 0.8, Tn, that is 6, plus 1 minus 0.8 into 10. So this comes out to be 6.8. Now next time tau n plus 1 is equal to alpha, Tn becomes 4, 1 minus alpha, tau n becomes 6.8, right? And you will be able to find out the next tau n plus 1, that comes out to be 4.56. So these are the expected next CPU burst cycle, and accordingly we can select the minimum CPU burst for our process. But again, this is the predicted value, it is not the exact value, right? So next is priority scheduling. A priority number is associated with each process, that is an integer value. So for each process we allocate a priority number, and that number will be used in the deciding that which process will be having higher priority, right? The CPU is allocated to the process with the highest priority. We assume that smallest integer is equal to is giving you the highest priority. So again it can be of two types, preemptive and non-preemptive. SJF is a priority scheduling where priority is the predicted next CPU burst time, right? So SJF is also a type of priority scheduling in which the CPU burst time is acting as the priority number. Smallest CPU burst cycle will give you the highest priority, right? In this case, the problem may be of starvation. Starvation is a situation when a process will never get executed, right? There is a chance that it may execute at some point of time, but it will never be able to execute. The process is not deadlocked. We are not saying that this process will never be executed. Definitely. No. There may be some chance that a process will be executed, but we don't know when it will get executed. Right? So this situation is called as starvation. So a low priority process may never execute. Again and again, suppose a process in a system, every time a process is submitted with the higher priority than all the existing processes. So in this case, the newly submitted process which is having highest priority will executed at that moment, and the processes with the lower priority will never get executed in the next time, right? So starvation problem may arise in case of priority scheduling. Solution of this can be the aging. As time progresses, increase the priority of the process which is of lowest priority, right? So at some point of time, the lowest priority process will also get its turn to be executed, right? Next one is the round robin. So processes are executed in FCFS manner for a time quantum each time. We arrange all the processes in the FCFS manner and assign a time value to each process, right? So there are three processes P1, P2, P3, and we say that time quantum value is 2 and their arrival time is P1, then P2 and then P3. So we arrange these processes in FCFS manner P1, P2, P3, and each process will be executed for 2 units of the time. That is your time quantum, right? So first P1 will be executed for 2 seconds, then P2 will be executed for 2 units, then P3 will be executed for 2 units, and then P1 again will be executed. So after the expiry of time quantum of a process, it is preempted and added to the end of the ready queue. So when P1 process executed for 2 units of time, it will be preempted by process P2, and this P1 process will be submitted to the end of your ready queue, and at the end P3 process was there, so P1 will be added to the end of or to after the process P3, right? Is it okay? So performance is like when queue is very large, round robin becomes FIFO, right? If queue is very small, so your system will be doing context switch only, right? So queue must be large with respect to context switch, otherwise overhead is too high. Overhead of what? Overhead of context switching. You say it takes 2 milliseconds to happen a context switch to switching from process P1 to P2, right? And you assign your time quantum value as 0.5 millisecond. So only 0.5 millisecond is For 0.5 millisecond your CPU is executing a process, and then for 2 millisecond it is doing the context switch, and context switch is not the useful task. No instruction of your process is executed while context switch takes place, right? So useful work is done 0.5 milliseconds out of total 2.5 milliseconds. So utilization is very low in that case. If you put your time quantum value to be very small as compared to context switch time, right? So Q cannot be very large and it should not be very small also. So there has to be a trade-off between this Q and your time context time, right? So let's have an example for this. These are the 4 processes and their burst time are given. So processes arrive in the order P1, P2, P3, P4 at time almost 0, considering round robin scheduling algorithm with the time quantum equal to 20. So time quantum is given as 20. Draw the Gantt chart for the system and calculate average waiting time, average turnaround time and average response time. So first one, P1 will be executed for 20 seconds and its remaining time is 33 seconds. Then P2 will be executed for 17 seconds. Now its allocated time quantum is 20, but P2 is finished before its allocated time quantum. So once P2 is completed, immediately P3 will start its execution. It will not wait up to end of 20th second, right? Then P3 will be executed for 20 seconds. Then P4 will be executed for 20 seconds. Then again P1 will be executed like this. So P1 first executed for 20 seconds, then P2 executed up to 37 because P2 burst time is 17 seconds only. So P3 will start at 37 and will execute for next 20 seconds. Then P4 will start its execution at 57 up to 77. Then P1 will execute for next 20 units of the time. P2 was finished. So then P3 will be executed and then P4 and then again P1 will be executed for 13 units of the time, then P3 and then P3 again, because P3 is the only remaining process at the end. So P3 will continue its execution up to termination, right? So average waiting time is equal to, for process P1 in the starting 0, at this time 0, then it leaves the CPU at 20 and again gets the CPU at 77. So 77 minus 20, that is 57, and then again it leaves the CPU as 97 and it waits up to 121. So 121 minus 97, so this is not 124, it should be 24 only, right? 121 minus 97, that is 24. Then for P2 it submitted at time 0 and it gets the CPU at 20. So 20 is the waiting time for P2. For P3 in the starting 37, then 97 minus 57, that is 40, and then 134 minus 117, that is 17, plus 4p4 in the starting 57, and then 117 minus 77, that is 40, divided by 4 equal to 98. Average turnaround time for P1 is submitted 0 and it completes at 134. So 134 is the turnaround time of P1. Then P2 was submitted at 0 and it completes its execution at 37. So 37 is turnaround time of P2. Then for P3 is terminated at 162 and was submitted at 0. So its turnaround time is 162, plus for P4 its completion time is 121. So 121 divided by 4 is equal to 113.5 is the average turnaround time of the system. So average response time for P1 it is 0, for P2 it is 20, for P3 it is 37, for P4 it is 57, and that comes out to be 28.5, right? So time quantum and context switch time can be understood better in this case. Say time quantum is 12, so up to 10 total 0 context switch will take place, right? If we take the process time of 10 units, so and time quantum unit is 12, so only 0 context switch takes place, no context switch, only the CPU process execution takes place, right? If we take time quantum at 6, so one context switch takes place at 6 seconds. If we have time quantum as 1 unit, then total 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's all. So total 9 context switch will take place. So if we say that it takes TC time for context switch, so in this last case total context switch time is equal to 9 into TC, whereas in second case it is only TC and in first case it is only 0, right? So this is how when you increase your your time quantum value, your context switch decreases and hence context switch time is also decreases, but your system is going towards FCFS scheduling policy, right? The next is multi-level queue. So ready queue is partitioned into separate queues for foreground processes and background processes. So we can put interactive processes into foreground queue and batch processes into background queue, because background processes are those processes which do not require any intervention of the user or which does not require any user support, right? So those processes can be submitted in the background, and the processes which require some user input or some interaction from the user, those can be submitted to the foreground queue, right? So each queue has its own scheduling algorithm. It can be round robin, FCFS, priority, SJF, anyone, and scheduling must be done between the queues. Fixed priority scheduling, that which queue is having the highest priority, which queue is having the lowest priority, or we can execute or we can assign them some time slice according to their priority, that highest priority queue will be executed for 80% of the time, and for 20% of the time your background processes or the lower priority queue will be executed, right? So like this we can have multiple queues with our system, and within queue we can assign some scheduling policy, and between queues again we can assign some policy that for how long your highest priority q1 will be executed, and for how long another queue of low priority will be executed, right? So this can be one example in which we have 5 queues in the system. So whenever a system process will be submitted to the ready queue, it will be submitted in the highest priority queue, and interactive processes will be submitted to second highest. Interactive editing processes may be submitted to third highest. Batch processes can be submitted to fourth highest, and student processes can be submitted to the lowest priority queue. The The point here to note is that a process will remain in the same queue in which it has been submitted initially. A process is not allowed to change the queue once it is submitted to the system, right? So in this case we have highest priority of the system queue processes, then interactive processes, then interactive editing processes, then batch processing, and then student processes. Now it is not fixed that we should have the priority in this order only. It totally depends on your operating system implementation. For what purpose you are trying to implement the operating system, for what purpose or for what objective or what is your target audience you are trying to target, it totally depends on that, right? So it is system dependent that which queue or what processes will be submitted to which queue with highest priority, and which processes will be submitted to the lowest priority queue. So among these queues we may have some policy that how these queues will be submitted into the CPU, and within a queue what will be the scheduling policy. So a system processes can be executed in FCFS manner, interactive processes can be executed in round robin manner, interactive editing process can be executed in some priority scheduling, batch processing can be executed in FCFS, or student processes can be executed in the priority order or SJF order, right? So there may be different policies for each queue, and among these queues there may be some policy so that we can decide that which queue will be executed for how long, right? So this is the multi-level queue scheduling. We have divided our processes into some categories, and according to their priority we can assign them some queue, and these queues are also having some order of their priority, right? But again the point here to note is that a process will not be allowed to change its queue during its execution. The process will be remain in the same queue in which it was submitted until its termination, right? So again there may be issue of some starvation in this case, that the lowest priority queue will never gets executed, right? So to solve this problem we may have multi-level feedback queue. So in multi-level feedback queue a process can move between the various queues. Aging can be implemented this way. Aging is the solution to the starvation problem. As time goes, we increase the priority of a process which is waiting for very long duration, right? So that this process never goes to starvation state. So this is called as multi-level feedback queue. A process which is submitted in lowest priority queue may be shifted to the high priority queue as time passes, right? So multi-level feedback queue scheduler defined by the following parameters, that is number of queues, how many number of queues are there, scheduling algorithm for each queue, within queue which scheduling policy will be executed, method used to determine when to upgrade a process, that is solution of aging, method used to determine when to demote a queue or demote a process, method used to determine which queue a process will enter when that process needs some service, right? So these are the parameters which we have to decide for multi-level feedback queue scheduler, right? So here is an example. Suppose there are three queues, Q0, Q1, Q2. Q0, in Q0 a process will be executed for 8 milliseconds. In Q2 a process will be executed for 16 milliseconds. In Q3 processes will be executed in FCFS manner. And scheduling is a new job enters Q0 which is served FCFS. When it gains CPU, job receives 8 milliseconds. If it does not finish in 8 milliseconds, job is moved to Q1, right? At Q1, job is again served FCFS. That means if multiple processes are there in Q1 queue, then they will be executed in FCFS manner. So within queue, we are executing the processes in the FCFS manner, and a process will be executed for 16 milliseconds in the Q1, and then it will be moved to Q2 if still some time is required to execute further, right? And in Q2 there is no limit on the time quantum. So this can be the diagrammatic representation of the system, in which this is our Q1, in which time quantum is 8 seconds or 8 milliseconds. So a process will be executed at max for 8 milliseconds in Q0, then it will be further submitted to Q1. Here it will be allowed to execute for 16 seconds, 16 milliseconds, and then further it will be submitted to Q2, in which it will be executed in FCFS manner, right? So this is how multi-level feedback queue works. Then multiple processor scheduling. If we have multiple processors, then how scheduling will be performed? So CPU scheduling is more complex when multiple CPUs are available, because it's easy to implement scheduling policy on a single CPU, because there is only one resource which will be shared among multiple processes. And if we have multiple processors also in our system, then we have to keep track of all the processes which are running on different CPUs also, right? So on homogeneous processors within a multiprocessor, homogeneous processors means like symmetric processing, load balancing, we also have to take care of load balancing. There should not be the case that one CPU is overloaded and other CPUs are underutilized, right? In case of asymmetric multiprocessing, only one processor accesses the system data structure, alleviating the need for data sharing. In that case, a processor is acting as the master processor and other processors are acting as the slave processor, right? So data sharing may be required in that system. For real-time scheduling, hard real-time systems require to complete a critical task within a guaranteed amount of time. So in this case, we need to schedule the hard real-time problems with the immediate scheduling of these processors. Soft real-time computing requires that critical processes receive priority over less fortunate ones, right? And that's all. Here we complete our CPU scheduling chapter. Thank you.